Imagine you are trying to measure the length of a room. You use a tape measure, and it says the room is 10 meters long. Then you use a laser rangefinder, a completely different tool, and it says the room is 11 meters long. You assume you made a mistake. You check the tape measure. It's perfect. You calibrate the laser. It's perfect. You measure 1,000 more times. The tape always says 10. The laser always says 11. Now, imagine that room is the universe. For the last century, astronomers have had one main job: figure out how fast the universe is growing. We know the universe is expanding, getting bigger every second. This rate of expansion is called the Hubble Constant. It is perhaps the most important number in all of science because it tells us the age, the history, and the ultimate fate of reality. If the number is low, the universe is old and tired. If the number is high, the universe is young and violent. Here is the problem. We have two perfect ways to measure this number. One looks at the beginning of time, the echo of the Big Bang. The other looks at the stars around us today. Both methods have become incredibly precise. Both are considered gold standards of science. And they disagree. This isn't a statistical error anymore. The chance of this being a fluke is less than 1 in 3.5 million. It's called the Hubble Tension. It implies that either our measurements are wrong, which seems impossible after decades of checking, or something far more terrifying is happening. It implies that our understanding of the universe is fundamentally broken, somewhere between the Big Bang and today. The laws of physics changed. We are standing on the edge of a cliff. We thought we had the universe figured out, but the cosmos is screaming at us that we are missing something massive. Today, we are going to look at the crack in the foundation of physics. To understand why this is a crisis, we have to look at the old way. The map we've been using for 40 years. It's called Lambda-CDM. It's the standard model of the Big Bang. It says the universe is made of three things: regular matter 5%, stars, gas in us; dark matter 27%, invisible glue holding galaxies together; dark energy 68%, mysterious energy pushing the universe apart. This model is incredibly successful. It predicts everything from the distribution of galaxies to the ratio of hydrogen and helium. It's a beautiful theory, but a theory is only as good as its numbers. We need to know exactly how fast the universe is expanding to make the math work. So, we built two different rulers to measure it. This brings us to the discovery of the tension. Ruler 1, the early universe, by using the Planck satellite. This method looks at the baby picture of the universe, the cosmic microwave background, CMB. This is light left over from 380,000 years after the Big Bang. The European Space Agency's Planck satellite measured this ancient light with insane precision. It's like hearing the opening note of a symphony. By analyzing the sound waves in the early universe, we can calculate how the universe should have expanded over the last 13.8 billion years. The Planck prediction is extremely confident. The universe is expanding at 67.4 kilometers per second per megaparsec. Remember that number, 67. Ruler 2, the late universe, by using the distance ladder. This method doesn't look at predictions. It looks at observations right now. We use the Hubble Space Telescope to look at pulsating stars called Cepheids and exploding stars called Type 1a supernovae. These are standard candles. We know exactly how bright they are, so we can tell exactly how far away they are. By watching them move away from us, we measure the expansion directly. This team, led by Nobel laureate Adam Rees, checked their work hundreds of times. Their result is rock solid. The universe is expanding at 73 kilometers per second per megaparsec. Remember that number, 73. 67 and 73 are not the same number. The error bars don't touch. The early universe says the cosmos is growing slowly. The late universe says it's growing fast. If Planck is right, the distance ladder is broken. If the distance ladder is right, Planck is broken. Or both are right, and the universe accelerated somewhere in the middle for no reason. You might ask, maybe the astronomers just measured the distance to the stars wrong. Let me explain the mechanism of the cosmic distance ladder, so you can see why this is so hard to dismiss. It works in 3 steps, like stepping stones across a river. 1. Geometry. We measure the distance to nearby stars using parallax, basic geometry. 2. Cepheids. We find pulsating stars in those nearby clusters. We learn that pulse speed equals true brightness. We then find these same stars in other galaxies. Now we know the distance to those galaxies. 3. Supernova. In those galaxies, we find exploding white dwarfs, type 1a supernovae. These are huge explosions that always have the exact same brightness. We use them to measure the distance to the edge of the observable universe. The scientists have checked the dust. They've checked the telescope calibration. They've checked the math. The 73 number refuses to go away. The mechanism implies that the universe now is expanding 9% faster than the universe then predicted it would. It's as if you threw a ball, and instead of slowing down due to gravity or speeding up steadily due to dark energy, it suddenly got a cryptic turbo boost halfway through the flight. Something is missing from our model. So, where do we go from here? This crisis is driving the next 5 to 50 years of astronomy. The 5-year horizon, the judge JWST. Right now, the James Webb Space Telescope is rechecking the work. JWST can see Cepheid stars that Hubble couldn't resolve, separating them from the crowded background of their galaxies. Initial data from JWST, released just recently, seems to confirm the Hubble data. It's looking less and less like a measurement error. Over the next few years, JWST and the upcoming Nancy Grace Roman telescope will eliminate every possible excuse for human error. If the tension remains at 5 sigma, the gold standard for scientific discovery, we officially have to rewrite physics. The 50-year horizon, new physics. If the error is in the universe, not the telescopes, the implications are profound. 1. Early dark energy. Perhaps there was a brief flash of extra dark energy right after the Big Bang that faded away, giving the universe a kickstart we didn't account for. 2. Decaying dark matter. Maybe dark matter isn't stable. If it slowly turns into radiation over billions of years, the gravity holding the universe together would weaken, allowing it to expand faster, explaining the 73. 3. Modified gravity. Maybe Einstein was slightly wrong. On the scale of billions of light years, gravity might behave differently than it does in our solar system. This isn't just fixing a decimal point. This changes the age of the universe. It might be a billion years younger than we thought. It changes our understanding of how galaxies form. It changes the ultimate fate of the cosmos, whether we freeze, rip, or crunch. We like to think of science as a steady march toward truth. We build a map, We fill in the blanks, and eventually we know everything. But the Hubble tension reminds us that the map is not the territory. We are measuring the universe with our best tools, our brightest minds, and our most beautiful math. And the universe is looking back at us and saying, "You don't understand me yet." There is a dark side to this. If we are wrong about the expansion rate, what else are we wrong about? We infer the existence of dark energy and dark matter based on these expansion models. If the model is broken, do those things even exist? Or are they just phantoms created by our bad math? We are living through a revolution. The comfortable era of cosmology is over. The crisis is here. So I have to ask you, do you think we just made a measurement error? Or is it time to delete Einstein's equations and start over? Let me know in the comments.